welcome everybody. We're just going to take a couple minutes while everyone files into this virtual meeting, and then we will get started. Thanks for joining us today. Should really get some background music for these times. For everyone just joining us, we're just going to take a couple minutes and let a few other people file in, and then we'll start hearing from Aaron. All right, Aaron. Well, if you're ready, I'm gonna go ahead and do a little intro here, and we can get going.
Yeah, let's rock and roll.
So thanks everyone for joining us today. My name is David Brown. I am with StratCann, a cannabis industry publication, and today we're going to be hearing from Aaron Godin, the co-founder and director of applied sciences at AGMS Solutions. He's going to be giving a talk on the importance of mass balance from field to gummy. Really looking at critical value ingredients and how they are affected by processing and refinement through the processing process. So with that said, I'm just going to hand it over to Aaron. If you have any questions throughout the event, feel free to just throw them up in the chat or raise your hand or put them in the QA, and I can toss those over to Aaron while he's speaking. And then we will also have some time at the end in about 30 minutes or so where Aaron can field any other questions you may have. So with that said, I'm going to hand things over to Aaron, and he will get going. Thanks, Aaron.
Awesome. Thanks for the intro, Dave, and thanks for giving me the opportunity to do this. So I've been in the cannabis industry in various roles since about 2014. Prior, I was a soil scientist, and I looked at how nutrients are cycled through soil and how they're affected by different microbial processes. I'm currently co-founder and application scientist with AGMS Solutions Inc, as David mentions. We provide processing solutions for extraction and refinement in natural products. And whether I'm helping customers select the right process, or I'm helping a customer optimize an existing process, or doing R&D on novel products, really a lot of what I do comes down to understanding how ingredients are affected by different processes. And that's what I'm going to talk to you guys about today. So just a brief overview of what we're going to be going over. We're going to take a quick look at cannabis and its constituents. We're going to look at processing from the field to isolate. And then we're going to review the conservation of mass and how that applies to mass balance and process efficiency. And then we're going to use those theories to look at some top-down modeling and some bottom-up modeling. And then finally, we're going to finish the talk with some process optimization. So I'm not going to spend too much time talking about cannabis, as most of you probably understand what is in cannabis and how it's beneficial. But for the purpose of this talk, I'll just review briefly some of the beneficial compounds. So cannabis produces a ton of secondary metabolites. Between 300 and 500 have been identified. And secondary metabolites are chemicals that are not used in the growth or reproduction of the plant. It's believed that the plant produces the metabolites for defense, for example, to protect the plants from microbial infestations or to deter predation by insects. So of those secondary metabolites, there's over 100 identified cannabinoids. And cannabinoids are a class of molecules that associate with the cannabinoid receptors in our bodies. Of the endogenous cannabinoids, or the cannabinoids that are made outside of our bodies, most of them are found in the cannabis plant. THC and CBD, which we're all familiar with, typically make up more than 95% of cannabinoids in cannabis. Terpenes and terpenoids are largely responsible for the characteristic aroma of cannabis. Terpenes are hydrocarbons made up of varying degrees of 5-carbon isoprene units, which you can see here, that can be configured in many different ways. And they're classified based on the number of isoprene units. For example, myrcene contains 2 isoprene units and is classified as a monoterpene. I'm going to spend most of this talk discussing cannabinoids, but the same theories and tools can be applied to terpenes as well. Now, most of the metabolites, including the cannabinoids and terpenes, the secondary metabolites, are produced in these little factories called trichomes, and those exist mostly on the surface of the female flowers. They come in a lot of different shapes and sizes, but for this discussion, it's beyond the scope of this webinar, so we can talk more about that another time. So I pulled these 2 products from the BC Cannabis website about a week ago, this Dongle and Sunset. What amazes me is that up to 30% of the mass of a dried bud can be a single secondary metabolite. That is, up to 30% can be a chemical that is not involved in the growth or reproduction of the plant, which is pretty fascinating when you think about it. Now, if we were to take a fresh harvested bud and we were to mash it up and separate it into its constituents, what do we see? Well, we're probably about 70% water, maybe less than 10% cannabinoids, less than 2% terpenes, and the rest is non-volatile components such as fat and cellulose that are important components of plant life and reproduction. When we remove the water, we're increasing the concentration of most of those other constituents, including the cannabinoids and the terpenes, and the undesirable components as well. When we're talking about extraction and refinement and processing in general, we're really talking about getting the most of the value components, which we're going to talk the cannabinoids and the terpenes, out of the feedstock and concentrating them into something that's usable. So cannabis in Canada is processed into 3 categories: edible cannabis, cannabis extracts, either inhalable or ingestible, or cannabis topicals. I pulled some data from Health Canada Cannabis Market data website, which is made publicly available. And I took that data and I put it into a graph. So on the y-axis here, we have the number of units sold between October 2019 and March 2021 of both medical and non-medical products. And on the x-axis, we have the different categories of processed cannabis: edible cannabis, extracts, and topicals. And so in Canada from that time, over 21 million edible products, over 21 million extracts, and over 157,000 units of these items were sold. So there's a lot of demand for these products. Now there's dozens of ways that we can make cannabis into these different products. So let's look at how this is done. After some time of flowering, typically 8 to 12 weeks, the buds are harvested. Now, why do we harvest the buds? Well, we need to separate the flowers, which contain our cannabinoids and our terpenes, from the rest of the plant material. And the buds are harvested based on either physical or chemical characteristics, or both. For the rest of this discussion, I'm going to focus on a traditional set of methods for extraction and refinement, but please understand that there's other ways that this can be done. So after the buds are harvested, typically they need to be dried and cured. Why do we need to dry cannabis? Well, water is often an enemy of many extraction and refinement processes for various reasons. Materials typically dry to somewhere between 5 and 13%. And this is done by regulating the temperature and the humidity of the space that the cannabis is dried in. On the other hand, subjecting cannabis to temperature and low humidity will promote the loss of volatiles, including terpenes. So in some processes, we want to preserve the water, preserve the volatiles, and we'll freeze the products either with cryogenic fluid, or we can throw it in a freezer, subject to the products that you want to make and your downstream processes. So the next step is extraction. And why do we want to extract? Well, we want to separate the oils from the rest of the plant material. In simple terms, you can think of extraction process like making coffee. And so in my diagram here, I have a French press. You're putting your coffee beans into the French press. You're pouring in some hot water, which is a solvent. You let it soak for some amount of time, and then you separate the ground coffee beans from the extracted oils and water, and then you drink your coffee. There are a lot of different ways you can extract ethanol, CO2, butane, propane, isopropyl alcohol, methanol, hexane, heptane, water, rosin. I'm not going to say that one method is better than the other. It really depends on what your inputs are and what the desired end products are. I will say that the extraction process does affect your downstream processes. The next step is winterization. With winterization, we're trying to move the bulk of the undesirable compounds. And that's because our extraction process usually has co-extracted a bunch of these undesirables. And so here we have a traditional vacuum filtration setup on the left with a Buchner funnel, where we pour our solvent oil mixture into a funnel, and then we vacuum the solvent through the funnel. There's positive pressure filtration methods, such as using a bag filter, cartridge filter, lenticular filter. You can do a liquid extraction, where you're using the solubility of your oil and the solubility of different solvents to essentially filter out your undesirables. Or there's membrane filtration, where you're selectively filtering the fats based on molecular size relative to the size of the other compounds in your solution. And then we need to, because we've added solvent in extraction and winterization, now we need to somehow remove that solvent. Traditionally, this is done through some sort of a distillation process, where we have our oil and solvent in a boiling flask. You can see on the left here. We heat that boiling flask to the temperature that our solvent wants to evaporate. Our solvent evaporates, it condenses on a chilled coil, and it collects in a collection flask. You can see this used in many different types of equipment, such as a rotor evaporator or a falling film evaporator. These are just variants of solvent distillation equipment. You can also use membrane filtration to separate your solvent from your oil fractions. The next step in the process is decarboxylation, and that's where we're converting our acidic cannabinoids to their neutral forms. Most of the cannabinoids that are present in the plant material exist as the acidic forms and not the neutral forms. And this is done by heating the solution somewhere between 90 and 130 degrees Celsius for some amount of time. Why do we want to do this? Well, for number one, we want to activate our THC so that it's psychoactive. The acidic form of THC is not psychoactive, where the neutral form is psychoactive. Number two, there's some downstream processes that require a decarboxylated product. In other words, they won't work properly or efficiently if the product is not decarboxylated in the first place. And next, we're going to distill the winterized oil. And why do we distill? Well, we want to further increase the concentration of the cannabinoids in the oil. And with distillation process, we're essentially just selectively boiling our cannabinoids and we're leaving the rest of the material behind. And lastly, we can take that distillate and we can crystallize the cannabinoids from the distillate mix. And this is usually done by mixing your distillate in a nonpolar solvent, reducing the temperature, and then precipitating the cannabinoids and separating them from the liquid mix with some kind of vacuum filtration apparatus. So we're going to just spend the rest of the webinar discussing how our value compounds, our cannabinoids or terpenes, move through these processes. But before we can get into that, I'm going to introduce a couple of concepts. David, did you have a question?
I believe someone had raised their hand. I was just trying, I think Tyler Davies, I was just trying to see what their question was. Not sure if they could put that in the chat. Anyway, I'll let you continue. Sorry, Aaron.
Sure. So I'm going to introduce a couple theories here. The first is the conservation of mass. And the conservation of mass says that in a closed system, matter is neither created or destroyed. Now you're probably wondering why I have a picture of a sandwich here, or maybe you're not. I mean, it's close to lunchtime where I am. A sandwich will have the same mass as the mass of its ingredients. So if you have 350 grams of ingredients, you're going to have 350 gram sandwich. Simple enough. Now, if we take that sandwich and we light it on fire, you may have now a 300 gram sandwich. But if we have that sandwich in a closed system, then you'll see that the other 50 grams went to water and carbon dioxide. And if we take that 300 gram roasted sandwich and we dissolve it in a strong acid, the sandwich and the acid will be the same mass as the sandwich and the acid separately. And so the theory of mass balance is an application of the conservation of mass. And mass balance is a consideration of the inputs, outputs, and distribution of a substance between streams in a process or stage. By the law of conservation of mass, the mass that enters a system must leave the system or accumulate within the system. And we can use a mass balance to measure the efficiency of a process. So say we have 100 grams of an input and we put it in a process and then we measure the mass of the output. We can measure the mass, or we can measure the efficiency of that process by dividing the end mass by the start mass. In this case, we have 100 grams at the start and 100 grams at the end. Our process efficiency is 100%. In this example, if we have 100 grams at the start, goes into our process, and we have 75 grams at the end, then our process is only 75% efficient. So you may be thinking, where did that extra 25 grams go? Well, remember that the mass that enters the system must leave the system or accumulate within the system. So perhaps 15 grams is trapped somewhere in the process, or perhaps 10 grams left the system somehow. So how do we measure process efficiency? We'll get to that later. So let's apply these theories to a real example. And I'll preface this conversation by saying there's going to be some degree of uncertainty with the estimates that we're going to talk about, but the more data that you can gather, the more accurate these models are going to be. So question, how many CBD gummies can you make with 1 acre of hemp? Well, first we need to understand more about the overall inputs and the outputs. What is the CBD content of the hemp feedstock? What is the expected dried yield of an acre of hemp? What is the size of a gummy? What is the desired concentration of a gummy? So let's say that our CBD content of our hemp feedstock is 10%. The expected dried yield of an acre of hemp is 1,000 kilograms. The size of a gummy is 2.5 grams. And the desired concentration of the gummy is 10 milligrams per gram, or 0.1% weight by weight CBD. Next, we need to calculate the available compound of interest. And when I say available, I mean the total amount that is available for processing. So if we have 1,000 kilograms of feedstock, we multiply that by 10%, we have 100 kilograms of available CBD in our acre of hemp. So does this mean we have 100 kgs of CBD going into our gummies? Not quite. In reality, we have to consider some amount of loss. So I'm going to take my 100 kilograms of CBD in my hemp, and I'm going to extract that hemp with whatever extraction chemistry I decide. And I'm going to say that I'm extracting 90% of that 100 kilograms of CBD. So I do my extraction, and then in my crude extract, I have 90 kilograms of CBD. And then I'm going to take my crude extract, and I'm going to do winterization and solvent recovery. And I'm going to say that that process is around 92% efficient. So I take my 90 kilograms of CBD in my crude oil, and I multiply it by 92%. And I'm left with 82.8 kilograms of CBD. So I have 82.8 kilograms of CBD in my winterized oil. And you'll notice that as we continue through processing from extraction all the way to gummy, our end product of each process is going to get more and more concentrated. And then I'm going to take my winterized oil, and I'm going to decarboxylate it, and I'm going to devolatize it. There is typically no loss associated with this step if you're measuring total CBD or total THC. What is important to note, though, is that perhaps some of your cannabinoids might convert into other cannabinoids through the application of heat in this process. So that's just something to note. And then I'm going to take my decarbed and devolitized oil, and I'm going to distill it. And let's say my distillation process is 80% efficient. So I take my 82.8 kilograms, and I multiply it by 80%, and I'm left with 66.24 kilograms of CBD in my distillate. And my distillate is probably going to be somewhere between 85 to low 90% cannabinoids. And then I'm going to take my distillate, and I'm going to crystallize it. And we're going to say my process is about 80% efficient. So I have my 66.24 kilograms of CBD in my distillate, and I multiply that by 80%, and I'm left with 53 kilograms of CBD in my isolate. And it's going to be probably around 98, 99+% CBD, my isolate. So how many gummies can we make? Well, first we need to calculate the mass of CBD in a single gummy. So 2.5 grams times my 10 milligrams per gram equals 25 milligrams CBD per gummy. Then I'm going to convert that to kilograms. And then I'm going to divide the mass of my CBD in the isolate by the mass of CBD in a gummy. And I can make 2,120,000 gummies. If I have 5 gummies per package, then I have 424,000 packages of gummies at 2.5 grams a gummy and 10 milligrams per gram CBD each. So to summarize, we started with 1,000 kilograms of hemp at 10% CBD, or roughly 100 kilograms of CBD. And we processed that down to isolate, where we were left with 53 kilograms of CBD. So you'll notice that as we go through our process, each step of extraction and refinement, we are losing some mass of our value ingredient. You also notice that the potency of the product increases as we go through our process chain. So a little trick, if you want to estimate the mass of a product at a given step, you just take the mass of cannabinoids or your value ingredient at that step, and you divide by the expected potency. So for example, if I have 66.24 kilograms of CBD in my distillate, I would estimate that my distillate is 90%. So I take 66.24 and I divide by 90%, and then I get 73.6 kilograms of distillate at 90%. So let's look at some bottom-up modeling using mass balance. So how much cannabis do I need to make 25,000 vape cartridges? Well, again, first we need to understand more about the overall inputs and outputs. How much oil is in a vape pen? What is the potency of the vape pen? And what is the potency of the cannabis feedstock? So we'll say that the vape pen has 0.5 grams of oil. The potency of the vape pen is 850 milligrams per gram, or 85% weight by weight THC. And the potency of the cannabis feedstock, we'll just estimate at 15%. Next, we need to calculate the mass of THC in our vape pens. So we take our 850 milligrams per gram, or 85%, and we multiply it by 0.5 gram vape cart, and we get 0.425 grams of THC per cart. We take that 0.425, we multiply it by the total number of vape carts, 25,000, and we calculate that we need just over 10 kilograms or 10.5 kilograms of THC. So this will be similar to our top-down modeling, except we'll be going backwards. Instead of multiplying by the process efficiency, we divide. So I take my vape cart, and the first step is probably formulation, but I'm going to assume that my formulation process is 100% efficient and I didn't lose any of my distillate in the formulation process. So I have 10.625 kilograms of THC in my distillate. And then I go through my distillation process and I say that that process was 80% efficient. So I divide by 80% and I have 13.28 kilograms of THC in my decarbed oil. Again, we're going backwards here. And then we're saying my decarb and devolatize step was 100% efficient. So now I have the same mass, 13.28 kilograms of THC in my winterized oil. Remember, my winterized oil weighs more than that. That's just the mass of THC in my winterized oil. And then I divide my by my extraction efficiency, which is estimated 90%. And we have 14.76 kilograms of THC in the crude extract. Sorry, in the last step, we're dividing by the winterization efficiency, 90%, not the extraction efficiency. Now I take my crude oil and of 14.76 kilograms of THC, and I divide by my extraction efficiency, and I get 16.39 kilograms of THC in my cannabis feedstock. And so to calculate how much cannabis that is, I divide by the potency of my cannabis feedstock, which at the beginning we estimated to be 15%. And we calculate that we need almost 110 kilograms of cannabis at 15% THC. So to summarize, To make our 25,000 vape pens, we need just over 10.5 kilos of THC, which we use from distillate. So as we work backwards through our process, we calculated that the 16.3 kilograms of THC in our starting feedstock worked out to about 109 kilograms of cannabis at 15% potency. So now that we've looked at how process efficiency affects our cannabinoid concentrations, let's revisit process efficiency. Any questions so far?
Nothing so far.
Okay. So in order to understand how to measure process efficiency, it's very important to understand how to read data on a C of A or a certificate of analysis. And this is the document that you're going to get from your testing lab when you're testing the potency of your material. So just be very mindful of the units of measurement. mg per g, milligrams per gram. 1 milligram per gram equals 0.1%. Milligrams per milliliter, milligrams per milliliter is used for solutions. But keep in mind, 1 milligram per milliliter does not always equal 0.1% if the density of the solution is not 1 gram per milliliter. Percent weight by weight is the relative amount of solute present in a solvent. 1% weight by weight equals 10 milligrams per gram. You have percent weight and other units of measurement that you might see, parts per million or parts per billion, micrograms per gram and nanograms per gram respectively. So for example, if we test a gummy at 23 milligrams per gram, and we want to know how much CBD or cannabinoid is in a 3-gram gummy, then we simply multiply the mass of our gummy by the concentration. In this case, 3 grams times 23 milligrams per gram gives us 69 milligrams of CBD. And I just wanted to highlight again, be mindful of your milligrams per milliliter to milligrams per gram conversions. 1 milligram per milliliter will not always equal 1 milligram per gram depending on the density of the solution. So recall that we defined process efficiency earlier on as the percentage of compounded interest that is retained at the end of a process. We take the end mass and we divide by the start mass and we multiply by 100. But how do we actually measure process efficiency? It really depends on the process. So let's take extraction, for example. There are 2 ways that we can measure extraction efficiency. In the first method, we're going to calculate the efficiency by estimating what was extracted. So we have 100 kilograms of plant material that's loaded into this extraction column here. And we test the material and we find out that we have 20% cannabinoids up at the top here. So to calculate the amount of the mass of cannabinoids, we take the total mass of material, 100 kilograms, and we multiply by the potency of the material, which is 20%, and we calculate that we have 20 kilograms of cannabinoids in our extractor. So that's the available cannabinoids. Next, we perform our extraction and we measure the mass remaining in the raffinate material. And the raffinate material is the material that's left over in the extractor. So we take the total mass of that material, 40 kilograms, and we multiply it by the potency of that material, 5%. And we learn that there's 2 kilograms left in the extractor that was non-extracted. Next, we calculate the difference between the starting mass and the finished mass and divide by the starting mass. So this gives us the theoretical percentage of what was extracted. I'm saying theoretical because we haven't actually measured what was extracted in a crude oil. We've only measured really what was removed from the extractor. And in the second method of measuring our extraction efficiency, we're measuring the actual extraction efficiency by comparing the mass in the extract to the initial starting mass. So again, we calculate the mass of cannabinoids in our extractor, which we have as 20 kilograms. And then we calculate the mass of cannabinoids in our crude oil here, which is 18 kilograms, or the weight of the oil times the potency of the oil. And then we divide the mass of cannabinoids in our oil by the mass of cannabinoids in the starting extractor. And that gives us our actual extraction efficiency. You guys still with me? So I wanted to use a second example of a white film distillation. Now, in a white film distillation, our objective is to separate the cannabinoids from the rest of the components in the oil. Typically, this is achieved in what we refer to as 2 passes, or 2 distillations performed under different pressure temperature conditions. So in the first pass, on the left, we're going to use a relatively low vacuum and higher boiling point temperature to strip the volatile terpene fraction from the oil. In the second pass, we're going to increase our temperature and use a deeper vacuum, and we're going to boil off the cannabinoid fraction. It may seem complicated, but at the very least, understand that there's one input to this process and there's many outputs. So to measure the overall efficiency of this process, we simply just measure the inputs and the outputs and our output of interest. And so in this case, our input, we have 1,000 grams at 600 milligrams per gram, or we have 600 grams of cannabinoids that are available. And then we measure our output distillate. And so we have 565 grams of that distillate at 850 milligrams per gram. So we calculate that to be 480.25 grams. If we divide that finished mass by the start mass, we learn that our process is 80% efficient. In other words, we have 80% of the cannabinoids in our distillate, and the rest are somewhere in the rest of this process. And we can use this data along with other data to optimize our process. Now, what do I mean by process optimization? Well, we can increase the efficiency of the process, which is what we've been talking about. We can reduce the time of the process. We can increase process repeatability. We can reduce the cost. We can reduce energy consumption. We can reduce waste. Here, I'm going to focus only on process efficiency, but much of what I'm going to talk about applies to other forms of process optimization as well. And there are 2 ways that we can look at increasing process efficiency. What I'm going to call inter-process optimization, or within process optimization. And we can look at the process itself. With inter-process optimization, we're looking at the variables that we can manipulate within the process. So perhaps it's the process parameters: temperature, pressure, agitation, oxygen level, pH, radiation, sound, charge. Perhaps it's the time. The time is influenced by the flow rate, or perhaps the residence time of the solution in one part of the process. Perhaps it's our inputs. So the feedstock inputs, the chemical or physical characteristics of that feedstock. Perhaps it's the reagents that we add as inputs: solvents, acids, bases, buffers, enzymes, etc. Perhaps it's other components within the system. Maybe there's byproducts that are building up as part of our process, like CO2 or APIs, or perhaps there's components in that process that we can swap out. So filter membranes, media, etc. Ultimately, it comes down to understanding the variables within your process and then testing your inputs and outputs. So recall the distillation example that we just looked at. We want to figure out how to increase our process efficiency. So we need to understand where our cannabinoids are going. We know that 80% of our cannabinoids ended up in our distillate. We don't know where the rest went, so we need to test the other outputs. So looking at the first pass, we measure our residue fraction, which is the fraction that goes into our second pass. We can see that we're about 91% efficient. Now, where's the loss? Well, we can see our two other output fractions, our volatile fraction and our distillate fraction. Our distillate fraction is about 75 grams and 470 milligrams per gram. So that's about 35 and a quarter grams of cannabinoids that ended up in our distillate fraction where they shouldn't be, or about 6%. Now, how do we minimize cannabinoids in the distillate fraction of our first pass? Well, we want to reduce the cannabinoids that are boiling. So intuitively, perhaps we reduce the vacuum, or we reduce the evaporator temperature, the boiling temperature, or maybe we increase the feed rate, so we make the machine run faster, or perhaps we decrease the wiper speed so that not as much of the oil has contact with the wiper basket. Now looking at the second pass, if we measure the residue fraction, we have nearly 70 grams or 11.5% of the cannabinoids not being boiled. And again, how can we increase the cannabinoids boiled into our distillate fraction? Well, intuitively, if we want to boil more things, we could increase the vacuum. We could increase the evaporator temperature. We could decrease the feed rate so the system runs slower. We could increase the wiper speed to enhance evaporation. All these things may encourage boiling. So the second way that we can look at optimizing a process is to alter the process design itself. So maybe there's more components that you can add to your process to enhance the process. Perhaps you need more heating, perhaps you need more cooling, perhaps you need larger or smaller vessels, perhaps you need to change the geometry of your vessels, or maybe you have selected the wrong process for your application, or perhaps there's a better process for your application. For example, I probably wouldn't use CO2 or water bubble hash to make live resin. You would want to select a process that's more suited for the application. Just understand that when you make a change to a process, you can affect the downstream processes or even the final product in itself. So to summarize, we looked at the conservation of mass and how we can use the conservation of mass to perform a mass balance on a process or system. Mass that enters a system must leave the system or accumulate within the system. And we can use this to calculate a process efficiency, which is the percentage of compound of interest that is obtained at the end of the process. We can use these theories to do top-down modeling, bottom-up modeling, and finally to do process optimization with our process and our products. And with that, I want to thank David Brown and Heather at StratCann for giving me the opportunity to do this webinar, and also my partners at AGMS Inc. Thanks.
Okay, and does anyone have any questions they want to toss up in the chat today? I'm not seeing anything in the chat, Aaron, but we can wait a few minutes and see if anyone has a chance to chime in.
And if you guys have any other questions or comments, feel free to email me. My email's here below my ugly mug.
And we'll also be posting this in the next few days. This has been recording, and we'll put it up on the website and on my social media in the next few days. So if anyone wants to missed any pieces or wants to play this back, they'll have that opportunity.
Awesome.
Okay, well, if there's no more questions, I'm just going to wait one more minute, but then we are just going to end things. So thanks again for everyone for joining. I'm David Brown with StratCann. This was Aaron Godin giving his talk, and we will be back again soon.
Well, it looks like we might have a question here from Stephanie.
Yeah, that'd be great, actually, if you could tell us about AGMS.
Yeah, so AGMS Solutions Inc., we offer process solutions for extraction and refinement of any natural products. So we essentially do A to Z solutions. So if you're starting a new business and you have some goals in mind with extraction and refinement, then we help you get there. We do facility design, we do equipment procurement, we do process optimization, SOP development, method validation, and also solvent distribution as well. And you can check us out at agmsinc.com.
Aaron, how, in terms of a lot of the stuff you're talking about with extraction, I feel like that is largely applicable to pretty large scale extraction approaches.
Absolutely.
Is it pretty reasonable to say that even if someone is doing pretty small scale extraction methods, that a lot of the math is similar?
It's very similar. You're going to use the same tools that you would use on a 10,000 pound a day operation that you'd use on a 1 gram a day operation. I mean, ultimately, it really comes down to, understanding what you put into the process and what comes out of the process, and then tweaking the process so that you can get more out of what you put in.
So I think Stephanie has another question to asking you if you can speak a little bit about testing of extraction products. So I imagine she means either potency or different analytical testing results.
Yeah, Stephanie, would you mind just clarifying what's, I guess, pesticides and raw material to extraction? So we really only focused in this talk on cannabinoids and following cannabinoids from feedstock to finished products. But anything that's in your cannabis feedstock could potentially be concentrated and carry over into the final product. And that includes pesticides as well. It really depends on what the solubility of those compounds are, whether it's pesticides or whether it's aflatoxins or whether it's heavy metals. What is the affinity of those contaminants with your solvent? That will dictate how that moves through your process, and also how are those contaminants affected by your process. Stephanie, is it kind of, did I walk around your question? You're welcome. Somebody asked, does AGMS work with solventless extraction? Absolutely, we do. We distribute some of that equipment, and we can do formulation and optimization with solventless extraction as well. We deal with every type of extraction chemistry under the sun. And if we don't know, we know somebody who does.
Okay, if that's all the questions, I think we're going to wrap it up. Stephanie, do you have anything else? All right. Do you have any final points to add, Aaron?
I don't think so. Again, if you guys have any questions or you're curious about anything that I've talked about, please reach out to me at my email, aaron@agmsinc.com. Happy to carry on the discussion further. And yeah, thanks, David. And thanks,
thank you, Aaron.
Awesome.
Very, very interesting conversation. I appreciate you sharing with us.
Thanks, guys.
All right. Bye-bye, everybody.